let's kick off. So what my talk's going to be about is low latency, and we'll find out why it's not actually about low latency later. This is sort of a review of what I learnt when I moved to London. I worked here in Perth 8 years ago with some of the guys in the room, and then I did the jump to London, and this is sort of me finding out what I didn't know that I didn't know when I went there. So hopefully it's a chance to demystify some of the things that happen outside of maybe if you're living in your own ecosystem here in Perth, what they're doing somewhere else, which is I thought kind of fun. Who am I? I wrote a book once, so some people know me about that, but we don't have time to cover this. I'm a dev at Cashies, I speak at things, and I run training on RX. If you've heard of that, if you haven't, come talk to me afterwards. I'm not a small town boy, never been to Detroit. I did, however, grow up in Auckland, New Zealand, so I'm another international speaker. I cut my teeth on ASP and Access, built a little club. I was a bit of a sport jock a long time ago and built the club's water polo website, which was really cool. That lasted 10 years, and I found out 10 years later, oh, they're still using that thing. That's cool. I graduated after doing Java, COBOL, C, VB5, and gladly took a role doing friendly old ASP with slightly scary SQL Server. I did that for a while. ASP.NET or .NET came out. I picked up ASP.NET, VB.NET. Yup, what up? SQL Server, kept that loving relationship with SQL Server going. That was really cool. Moved over to Perth sometime around there as well and picked up C#, continued with SQL Server. Felt like I'd done everything in the web space. We were just doing the same old thing over and again. And that's when I moved to Bankwest, in fact, and started doing WPF, WCF. And that's where things got really interesting. It was, hang on, I have to manage memory now? I never had to do that in the web. You just send a request and things happen, and something disposed, something garbage collector, and life was good, right? And then I moved to London, where WPF was actually a useful skill for me. And it was a bit of a case of, this is not, we're not in Kansas anymore. Where's the SQL Server? Where's the web server? No one's talking about WCF, and why is everyone always asking me about garbage collection, right? So I'd moved from sort of retail banking, though it was really just more crud application kind of stuff, to the world of high finance, trading foreign exchange, stocks, equities, pricing bonds and all this kind of stuff. And it was interesting, but it was just very odd that some things had just changed. So these are my top 10 things that I'd learnt on the way, so hopefully I can get them out to you quickly, because 10 things, 45 minutes, that doesn't give me much time to go through them. So the first thing I found out was know your targets. And I thought when I was going to move to London and they were all, there was this feeling of everything being super fast and it was going to be amazing, that hardware was going to be the secret sauce. I was like, oh, they're going to have some special routers or some Intel chip I've never heard of before. Wasn't the case. It was all about knowing your targets, and it was a balance between under-delivering, so just missing these targets that we hadn't thought about, or being those engineers that trace perfection and we just keep going and spend all the money until we've got this really fast thing, but actually haven't done all the other features yet. We've just made one bit very fast. And then the 3 M's of performance: measure, measure, measure. So hardware without targets. I thought this was kind of funny. Guy watches the Tour de France. He loves cycling on his daughter's bike in the driveway, sees Chris Froome and goes, you know what, I think I could do that. The only difference between me and him is the bike. Well, probably not, right? It's more than the hardware. You can't just throw hardware at a problem to go faster, and that's the point of that little slide. And then, so if it's not about hardware and it's about targets and measurement, the next question is measure what? And if you move on to that line of thinking, you're asking the right questions, you're in the right space. So let's just go through some terminology first, which I didn't quite understand these either at the time. So service time, the time to actually process the request. I'm like, cool, dictionary done, we know all the words now, that's all you need to know, right? Because if it's the time to, is there anything else to do? Well, actually there's latency, and this is probably the most misunderstood or misused word. When even the title of the talk, low latency, it's not low latency. Latency is the time spent waiting to be processed. So if I'm on a website and I click a button, The button, there'll be some JavaScript or something that happens, and then that'll send a request, but that'll get buffered on my network card. Then there's time across the wire, then it gets onto another network card, then it'll land in a queue on a server somewhere. The queue might be explicit, like 0MQ, in-service bus, something like that, or it might be an implicit queue, like a thread scheduler or something like that. But there are queues everywhere and there's latency everywhere. All of that time is not processing the request. That's getting my request to the bit of code that needs to process it. It's all time that's latent. So response time is the person clicking that button is what they see. The latency plus the service time is your response time. So that was interesting. I never really considered those three as a obviously you only need to measure two to get the other one. And then throughput is sort of the other side of the coin, is the rate at which requests or operations can be processed. Sometimes there's a false dichotomy about that. We won't talk about, there's not a trade-off between those throughput and response time, but some people mistake that there is. And then the next thing, I thought, okay, so we need to measure, and myself and quite a few of the other team made the common mistake of going, all right, well, let's get the median response time. That seems good. We should report the median response time. Well, if you report it, we should target the median response time. And what's the median response time as far as percentiles? It's the 50th percentile. And as engineers, now that we have a target so we know when to stop, when we get, say, 1 second response time as our median, we're going to stop, right? We've hit our target and we move on and do something else. What we'd actually be doing there is saying 50% of our users will get less than 1 second response time. What we're also saying is 50% of our users will get worse than 1 second response time. That seems like an odd target to have, doesn't it? So then maybe the mean is a better average. Well, the mean, anyone that's done statistics, you know you can make that whatever you want, kind of. Ascom's quadrant, 4 different sets of behavioural data shapes. These all have the same mean, but quite clearly if these were measurements taken from your system, they've all got different behaviours. And that takes me on to the point that I learned fairly recently, is you do not model your targets based on numbers, do we, Colin? We found this out about 6 weeks apart from each other. We model shapes, behaviours as shapes, okay? So here we have a non-linear percentile distribution. So here we've got 0, the next one isn't 10%, it's 90%. We jump straight to 90%. 99, and these are measurements of latency or response time or service time in our system. And I can see very quickly, because I'm not actually that interested in the 10, 20, 30, all the good results, I'm looking at the bad results. These are the problem areas. You can see here that this curve's not great. Even if it was linear, you'd know it's not that great. But because it's non-linear, we can actually see right and close where our trade-offs are. Maybe this line's good, but then the resolution's not great, but it actually bumps up over and there's a high line here. Maybe we actually want this line, something we can trade off with our client's input. And how do we collect this data? It's actually really interesting from a data collection point of view. You collect values in histograms. You measure the response time using hopefully a high resolution timer, and then you put that value in a bucket. So it was 1 second, you put it in the 1 second bucket. It was 2 seconds, you put it in the 2 seconds bucket. And by doing that, all you're really doing, the bucket just increments by 1. Assign it to that, and then your fidelity of your buckets becomes interesting. It's a fast and efficient way to store and record data, and there's implementations already existing. HDR histogram is a great tool for doing that, and produces charts like this, incredibly fast, tiny footprint. Wow, we're only up to number 2. Number 2, know your costs. Something I found really interesting working with, or being associated with some guys that were doing some high performance stuff. They all knew the cost, or had at least a vague idea of the cost of an operation in their system. So right down low level, basic operations, an increment, taking, this is measurements in nanoseconds, this is 1 nanosecond here. An increment and an addition, tiny, very quick, obviously, right? Multiplication, interesting, is an order of magnitude slower. Okay, that's interesting. Division, 3 orders of magnitude slower than an addition. Okay, that's just mildly interesting, but let's say we look at thread-safe implementations of these. Wow, division's actually not that expensive anymore, and atomic increments are expensive. And these are just measurements taken from my machine, your mileage may vary. But I found that performance engineers knew these costs, and they knew it for their platform. And maybe not specifically for adding numbers, but maybe hitting a network or writing to a disk, but they knew their numbers relevant to their system. They also understood that not everything is free. Just because it's one line of code doesn't mean it's as cheap as another line of code. Branching, inlining, locks and cast statements, they understood the difference and the cost trade-offs between each of these. I thought it was very interesting. So just for comparison, we had a quick look at that chart, and an increment and then a multiply was less than a nanosecond compared to, say, serializing, deserializing JSON in .NET, for example. We can only get about 8 seconds to do 1 million deserializations on this computer, for example. Just an interesting number to be aware of, 8 million, or 1 million 8 seconds. Okay, interesting. Other things this laptop can do, and I kind of think this is good to go back for me to think about context. I can every 2 seconds move 1 gigabyte of data off the disk on that laptop. It's a 2-year-old laptop. I think that's really impressive today that we can move that. With some pretty sophisticated software that's been written, I can push 41 million messages across a queue. 41 million messages in a second. That's pretty awesome, right? I can set up a 3-node cluster on 3 virtual boxes on this machine and push 660 durable messages to it a second. They're quite interesting numbers, and this isn't me boasting about how good this is or how clever I didn't write any of that, just giving you information on context, right? And so something else they do, because sometimes it's just too hard to think about nanoseconds, it's such a small number it sounds like it's free. You put it into scale, and when you think about 1 CPU cycle and compare that to memory access is cheap. Well, it's 6 minutes compared to the 1 second theoretical CPU instruction. And then we look at hitting the disk or human response time. Those scale numbers become very interesting, right? And human response time, 200 milliseconds, that's actually pretty quick, right? So obviously I'd rather my computer to be doing my algorithmic trading than a person clicking on a button. Now this is my number one. I kind of think you have to get to this one first, but this is the biggest takeaway, I think. Visualize your flows, know how your data and your instructions move through your system. So big O notation, people often refer to that only for like complex algorithms, low-level stuff like red-black trees or quicksort versus bubble sort kind of stuff. I think it's really applicable to high-level designs as well. I think this is a bit of a lost art, something that I think most of us would be guilty at, especially I am. And I'm going to play a game with you. I'm going to show you 3 flows, and I just want you to shout out faster or slower based on your gut feel if you think the next slide, when I show you the new slide, is it faster or slower than the previous slide? So just, you can almost cross your eyes and look at that. Is the next one faster or slower? Faster? Why? Just less. Good, perfect. Code's the enemy. Right, next one. Faster, right? Can I, some fairly damning quotes. I can think of no other field of human endeavor that allows levels of inefficiency we find acceptable in software. And it's so neat because I didn't say it, someone else did. Moore's law, I found it really funny that there's May's law as well, which is somehow we write software so crappy that we compensate Moore's law. Meaning that when I first moved here to Perth 10 years ago, everything still is slow, even though that's a beast of a laptop. So I'm going to quickly skip over O notation because I think we get what it is, I think. But as an exercise for the audience, and I really would love it if everyone did this, and if you did, tweet me later just so I know that someone did this. But on Monday, just grab a flow, any flow in your system, and just map it out, draw it out. And those flows I just showed you, websequencediagrams.com. It's like so easy a BA could use it. Draw a flow from your system and just get a feel for what your system actually does. And don't cheat. Don't go, oh yeah, then it just does this in the big method name. Detail what the method does as well. So which flow? I would say anything that takes more than a second. I'm going to be a bit mean here. If you've got a build, it takes an hour, 660 messages a second, okay? An hour, okay? That's taking too long. Got some unit tests that take 10 minutes, that's too long, okay? You need to, from check-in, be able to commit and put it in production in 15 minutes, absolute maximum, 15 minutes, right? So it takes you an hour to build, you've lost the game, you're 4 times out. Just a reminder, a gigabyte every 2 seconds. I just moved a gigabyte of data, right? 41 million messages a second. What is that doing for an hour? So on Monday, you got something like that, draw the flow, surprise yourself. And what we're going to do now is kind of scary. And I'm definitely not picking on anyone. Can we see this? Here we go. Is my mouse back? My mouse is back. Right. So I had a slider. Everyone know what I mean when I'm talking about a slider? A UI slider. And it was I had to drag it across and numbers added up. It was a personal loan amount. It's cool. But something had happened and it was like really juddery, and as I moved it, it was hard, and it actually hurt my hand because I just gripped my mouse harder. I was like, what's going on? So a couple of us got together and we put a timer around the method, the property we're setting in .NET, and it took 125 milliseconds to 250 milliseconds to do this. 50 milliseconds is the budget you get to update a UI. Anything after that is noticeable lag. We blew our budget by 5 times, okay? So we looked at this thing and went, well, okay, it's just a property. This is cool, I like this, early termination, that's easy. What's going on here? That was a collection of 3 things. It did a little loop. That was actually very cheap. We just set another property. That looks cheap. We refreshed something and then we set some events off. There's no problem here. What's going on? 250 milliseconds? And then I was like, well, let's dog food. I'm saying visualize your flows. So what I actually did was write down what we did. And a couple of us sat down and looked at it. And this is what it actually did. Every time I poked something, it poked another thing, and 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 it poked another thing. What the fuck is going on here? So, notice that there's some things out here. There's 8 of these as well. We call this expensive method 8 times, 17 milliseconds it was, which takes me back to my other point. Identify your critical path. So we saw this thing, it was taking too long, sat down with some of the other devs in the office, we figured out how to fix this, and we identified the critical path. You can't effectively optimize if you're not optimizing the critical path. Great book, it'll take you a weekend to read it. It's like a story, so it's fun to read. It's not like heavyweight Martin Fowler stuff. You identify it and then you focus only on that path. Now remember back on this thing, I've got that, takes 17 milliseconds. We could have done some things and shaved off 2 milliseconds, but we called it 8 times. So we got 16 milliseconds off. 16 milliseconds off 250 milliseconds? Oh cool, we're only blowing the budget by 4.5 times. What we did was reduce it down so the whole thing took just 2 calls of that. So okay, it still took 35 milliseconds, but we're under budget now, right? Identify the critical path, fix that, don't muck around with number 1 and 2. We could always go back and make that faster, but to what end? So you also notice that when you optimize the bottleneck, often what was number 2 isn't number 2 anymore. It's not even number 1, it's just gone because you just don't call it. Next, mechanical sympathy. Know the layer below which you operate. Jackie Stewart, Formula 1 champion, was worried in the 70s that designers and drivers were so specialized that they didn't really know much about what the other one did. So he coined the phrase mechanical sympathy as a term for the driver and the machine working together. Drivers didn't have to be able to build their race cars, but they had to have a general understanding of how the constituent parts sit together. And this is now becoming a feature in high performance computing or low latency computing. Just understand, I think it's applicable to all of us. If I'm a web dev, I should know what HTTP is and TLS and how the DOM works, right? Don't just throw HTML tags at the browser and hope. If you're a REST dev, and I mean the kind of integration guy, you're doing HTTP already, well then you should definitely know how TLS works and TCP and things like that. If you're a WPF dev, dispatcher, logical physical tree, and if you're working on any of the managed frameworks, so the big hitters, .NET, Java, JavaScript, please understand how your virtual machine works. So that's the CLR, the JVM or V8 generally. It gives you a good insight. Again, you don't have to build V8, but it's good to know how the thing works. If you're more in data area, know your page sizes. I found this really interesting. The people I was working with, they weren't talking about SQL Server, they were talking about cache lines, which was amazing. I was like, who cares what the cache line size is? But these guys did. If you're a SQL dev, you should know your page size because that impacts how you design your database. If you're a network guy, knowing how big your frame packets are, that can impact your design. If you're a bit twiddler, as I call them, knowing that a cache line is 64 bytes can impact the way you design things. And it was really interesting seeing a Stack Overflow on .NET recently about why does my 5-byte struct run slower than an 8-byte struct? 5 smaller should be faster. Why is that? Maybe something we can talk about afterwards. But it does require you to know your target platform. No point knowing what 2016 SQL Server does and then developing on 2005, right? Maybe they're different things. Know your target platform. And to Rob Moore's talk earlier, we should know the platform because we're always thinking about going to production, right? Hardware is cheap, devs aren't. In motorsport, if you can't afford 3 cars, you can't race. We should be doing the same thing. Don't play with one thing in prod, put all the money into prod. Foxy, remember that. Put all your money into prod. Oh, we don't have any money left to have the same thing in sit or pre-prod or dev. So you guys dev on SQL Server and we'll put an Oracle over there and what? It's madness, right? Hardware's cheap. You devs aren't, you're expensive. Question authority, which I thought was great because Rage Against the Machine. I'm born in the, grew up in the 90s. Like, yeah. So challenge conventional wisdom, but don't ignore it. And as a 90s rocker, I missed that part. It was challenged, not go fuck yourself authority. It was like question it, right? So TCP is the default. Well, to me, when I landed in London, of course TCP is the default. It's what keeps the internet working. Why would that be a bad thing? Congestion flow, ordering of messages, reliable, error check. These are great features to have. But there's a 3-way handshake and the header size is 20 bytes compared to say UDP, which is 8 bytes. So you kind of end up with this cool thing, which is probably what I would want if I was traveling across Turkmenistan, and I needed to survive. But if I was building a low latency system, maybe I would want that with no features and not pay the cost of all of that. So that was interesting. I found out that many, if not all, messaging systems in the low latency space were using UDP. Mind blown, right? No WCF out of interest. So C is faster, right? Challenge the conventions. Allows you to get close to the metal, which is cool, but it can dilute the focus. So there was an example where Silverlight team and C++ backend team that I worked in London, and we did have an exceptionally talented .NET team working on Silverlight, and the neckbeard guys were over there doing C++, and we're all very impressed, but from a distance because it's like they're smarter. Then we found out we had doctors and PhDs and C++ guys on the .NET team. And then after 18 months, we're like, that doesn't seem that fast what they're doing. I'm like, just doing basic math. I'm pretty sure they're off by an order of magnitude what they should be hitting. And so after a couple of drunken moments, we decided, you know what, we should give it. We spiked it, we presented it to the business. And in 9 weeks, 3 devs, and I say devs, they were outstanding devs, in C# produced the streamer, the low latency part of the system, that was 3 times faster than the C++ one. Interesting, challenge conventional wisdom. That wasn't impressive. What the guys are doing over in Java is impressive, right? We were just trying to copy what some Java guys are doing. If you get a chance and you don't already know it, look up Disruptor, Aaron, SBE, which are brought to you by Martin Thompson. Interestingly, his blog is Mechanical Sympathy, so obviously I've got a man crush on him. Todd Montgomery is his sort of partner in crime, actual NASA rocket scientist, mental. And then at the other end of the scale, instead of building libraries like this, which just destroy proprietary software and specialized hardware, and it runs on Java. Like, what is going on here? We've got guys like Gil who are producing JVM, so instead of using the Oracle one, use his one and your system will just go faster. Mental, right? Okay. Does it pay its way? Justify the costs of your features, your abstractions, and your libraries. So, if you're looking for performance, remember this is a performance talk, not a dogmatic you must do this. If you're looking for performance, maybe you don't want these in your system. Auto notifiers, auto routers, anything auto is doing the work for you. Maybe you want to code a little bit closer to the metal. ORMs, I like beating up on poor old ORMs. I kind of think of them as a compensating behavior for you have to use relational database and don't use CQRS, and I want it to look like a document database. It's like, how did that marriage all happen? Serialization choice. we all laugh if someone says, oh, let's use XML, but no one seems to laugh when you say JSON, which is still just a big fat text format. So protocol buffer is the de facto in most places, but is quickly getting eclipsed by these outrageously fast, more encoding than serialization formats. They're a little bit leaky, so generally you only use them in your LAN, but outrageously fast. There's SBE, for example, I don't think you can make it any faster. There's no more clock cycles you can drop off. It's pretty cool. And code reuse, I found this very interesting. Does it pay its way? Often code reuse gets mixed up as the goal. It's not a goal, it's an outcome of sometimes you design software and it works out and there's some code reuse, super. It is not the goal of what we're doing. Fast code is clean code. So what I find interesting is that we've got a group here of very interested and motivated developers because we took our Saturday off to do this. And we're probably all preaching OO, solid, DDD, CQRS. What was interesting was the low latency guys were actually practicing that. They weren't talking about it so much as actually doing it. And I thought, again, that the secret sauce is going to be something else. I thought this was just for us mortals, right? But the guys that were writing fast code were practicing all of that kind of stuff, especially single responsibility principle. Very interesting. And as an exercise, I'm just going to jump out and show single responsibility principle in action. Has anyone heard of RX? I don't think it's that popular in Perth at the moment. We don't do a lot of streaming of stuff. I'm a bit of a fan, and so is Brendan Foster. We both sort of contribute to the library. And I did a Perth change on it recently. There's a thing called a replay subject. Everyone know what a callback or an event is? You know, it's not a trick question. A replay subject basically means I can register for that callback or the event late and get previous values. That's kind of a neat feature. Temperature's changing, it's 27 degrees, it's 28 degrees, 29 degrees. If then there's a big gap and then I subscribe, what I really want to know is the current temperature, which really is just the last event. So I'd like a replay with a buffer of one thing. Sounds like a good tool. So we were looking at this thing and there was a problem. The guys were seeing performance that they didn't think was very good, 220 messages a second. I was like, that's pretty good. And they're like, yeah, but there's linear degradation. Double the subscribers, half the throughput. I was like, well, it seems like a trade-off. And they're like, seems a pretty expensive trade-off. So we looked at the code. A couple of us got together because we can't help ourselves. And let's just run a little example here. We say, we've got a subject, and if I put one thing through it, so a subject is basically a way to create a callback. I subscribe to it here and just give it a name, and I push some values through it, and I'll see subscriber 1 get them. Then I push a value after I subscribe for number 5. It's tiny. People see that at the back? Cool. So subscriber 1, because he subscribed early, got 1, 2, 3, 4. 5, and then subscriber 2, because he subscribed afterwards, he also gets 5. But what I want is subscriber 2 to also see the current value. So what I'm going to do is say I'd like a buffer of 1. Coding live is ridiculous. And then I'm going to say, yay, cool. So when I subscribed, I got that value of 4 because it was the current value. So that's not very clever, but it helps lead into what the problems were. So there's what the cost of subscribing was. It did some stuff, not too interesting for this talk. On next is the pushing of the value. So I'm putting it in, tell all the subscribers. Scheduled observer. So one of the other things you can do with the replay subject is not just tell me the last thing, you can tell me the last 2 minutes of things, last 10 hours of things. So there's a time component. I don't have a time component, I just want the last one. And then I stopwatch, what's this, what's that got? And then time interval. I've got all these time concerns in here. I'm not using the time version of this. And then I look at how it trims values before it pushes them. And there's a queue, and that's kind of nice, but hang on, I only want the last one value. Why would I have a queue in here? God, this seems like it's doing lots of stuff that I don't care about. And then we had a play and thought, you know what, we can make this a single responsibility principle. What the hell just happened there? So 1, notice the shape's different. We don't have that degradation. Every time I double my subscribers, very small impact. Right? To 4, again, we're still up here. Now take a look at the numbers. 220,000 messages a second, 50,000 messages a second, 10 million messages a second. Jump all the way out here, 16 things, we're still up in the millions. What happened there? So let's scroll down. That was the old implementation. Everyone remembered all of that? Whoa. This is what the new implementation is. It's a subclass, it's an abstract class, and it says, hey, add to the buffer, trim the buffer, then publish the values to the subscribers. I can read that. It's easy to read, it's clean. And then what do? I've got a replay one implementation of this. What do you do when you add a value to the buffer? There's no queue, there's no time, there's no locks. Yes, I have a value, and the value is this. What's the trim buffer? No op. I don't know what the concept of trimming the buffer is because I don't have a queue. When someone subscribes, if I have a value, you can have the value because it's already here. Nice and simple, right? So going from this kind of messy concern that had all the features, cool, we went to single responsibility principle. All this unnecessary code, interlocked exchanges, locks, spin weights, thread sleeps, mayhem, all went away, and we got 3 orders of magnitude speed out of that. So, GCs kill. GCs, what's that? Garbage collection. So, allocations don't kill, garbage collections kill, okay? Why and how? Going back to our previous example, I pushed 1 million messages through to 16 subscribers. 6,500 garbage collections. New implementation? 1 or 0 everywhere else. Okay, that's kind of interesting. All these allocations go away. Your expected GC pauses, something Joe Duffy recently was talking about. A Gen 0, talking nanoseconds. Gen 1, millisecond. Gen 2, 10 milliseconds. But I've heard of 17-minute pauses. And when your garbage collector runs on most systems, all threads stop what they're doing so it can mark and sweep. 17 minutes of no activity except for garbage collection. Going back to this, if I'm allocating at every if I'm garbage collecting every 150-second allocation, or on next, if I'm pushing out about 8,000 messages a second, which was what we were doing, I would be garbage collecting 52 times a second. Sounds like I'm not doing my work, I'm doing something else, right? So garbage collection for the win. Serialize, don't synchronize. I found this interesting too. Another thing that I was like, surely it's going to be all about hardware. No, wrong, it's about measuring. Next thing, surely concurrent all the things is going to be the next thing. It wasn't. I just thought everything was going to be like throw F# and more cores at it and it'll be fine. I was like, no, sit down, that's not a thing. So this was interesting, avoid contended resources. And we talked to SQL Server, we talked to Oracle, whatever, and we know that contending on that one big boy makes it hard, and the DBAs do fancy things to make it safe and all this. So we all have people poking at our contended resource, and I use Oracle and SQL as an example, but it could be any old resource. That could be the file system, that could be another web server or something. Instead of everyone contending on this, and this having a sophisticated locking strategy for its complex internal workings, do something else. Put a simple data structure in front of it, like a queue, contend on here, which is actually just contending on the tail, which is very simple to do. And now, okay, your contention cost here is like that. And what you can do is relax all your threading concerns, your locking concerns here, and this thing can run at full speed. It's like, oh, and that works? It really, really works. So single-threaded, interestingly as well, easy to code, easy to debug, easy to test. It's predictable by man and machine, which I found really interesting. So I can look at single-threaded code and go, yeah, I get what that does. All of us can look at that code I had up on the screen and go, add to buffer, trim buffer, push to, yeah, I get what that happens. If in between it was like mutex, semi-force, you're like, oh, I don't know what's going on there. But what's also interesting, predictable by man, predictable by machine. If your code's single-threaded and easy to understand, your CPU can start prefetching stuff. Disks, they stride through data very well. So if you are doing single-threaded and striding operations, your whole computer just heats up and starts doing what you want it to do, as opposed to heating up, shutting down, heating up, shutting down. Oh, hang on, I'm doing context switch. It just does what you want it to do. So uncontended single-threaded code can run extremely fast. So then, concurrency somewhere? Yes, concurrency, but maybe not at a process level. So instead of having a process with lots of threads all trying to do stuff, make a process dedicated to something. So in the finance space, I might have a process dedicated to buying and selling Netflix shares or American shares or something. You choose your level of parallelism. But the beauty about this is I can go, right, all Aussie dollar to Kiwi dollar can run on that process, and then I can put all the other lightweight currencies like ours on there, and then I can put British pound sterling and America on its own box, or I can have more of them running on their own box. If required, they tried not to do concurrency, but if required, instead of locks, consider lock-free or wait-free. And then consider your targets. Are you one thread that should be thread safe in case someone else does come along, two threads, so single producer, single consumer, or another thing. Circular buffers. I found this really interesting. I built one at uni and then thought nothing of it ever again. And at uni I also was a janitor, so that was fun. So for those who don't know, and I assume everyone does, it's just an array. That's all it is. And when you get to the end, you sort of wrap back around, and then it kind of feels like a circular buffer. The nice thing about these things is that the head and the tail become very uncontended. Taking something off this end doesn't really affect putting something on the other end. It's kind of nice. Constant space requirements, which is very nice for garbage collectors. You say, allocate this up front, and then I'm just going to keep using that same space instead of putting onto a mutating stack or queue, which may chew through allocations. Constant time to push and pop. That's nice for being predictable latency if it's constant time. And it's core to that now famous disruptor that the Java boys had produced that sort of outstripped the C++ boys, and now Java runs one of the fastest exchanges in the world, which again just blows my mind. Designed to run single code extremely fast, or more specifically single producer, single consumer, but can also work with multi-producer, multi-consumers and still be extremely fast. And number 10, performance culture. So if there's two takeaways for today, first was know your flows. Draw and visualize your flows. Try and find those sneaky things like that in your code. And number 2, the other thing I'd really like you to take away is this performance culture. Where there was performance, there was diligence. Whenever I met these guys or saw their code was clean. There was single responsibility principle in action. There were intention revealing interfaces. So when you looked at their code, you understood what it was doing. The language was tight, the domain was crisp. They used the right tool for the job and less code. Code was the enemy. If I had more time, I would have written less code, was the dogma that they were preaching. Very interesting. Compared to some of the other teams I worked on where frameworks are king, more code, how can we build an empire, right? That's not what these guys were doing. The primary concepts were not hidden. They weren't obfuscated by accident, and they weren't obfuscated by mess or dirty code, and they weren't obfuscated to protect the other devs. If it was a primary concern, it was put front and center. And if you wanted to play in that code base, you had to learn the primary concern, which probably meant you had to read one page on a wiki to get up to speed, but you were there to program on that thing, you understood it. A lot of care was taken to make sure that the core concepts remained the focus. So that meant build times were quick, tests ran fast, deployments were quick, they were repeatable. Generalized concepts that were distracting often got stripped out and put into other libraries, generally open sourced, which then became this virtuous cycle. So our build times got quicker because we're just pulling in an artifact instead of spending cycles building stuff. Someone else was looking at the open source thing that we pushed out, so that got faster and ran better. So it was like they fell into this virtuous cycle, and then all of a sudden they're doing something much better and faster than other people. And broken windows were fixed. Anyone heard of the broken window theory? Yes, good. So theory in criminology about norm setting and signaling behavior, generally around vandalism. You walk to work every day for a couple of years, and there's this one old tatty building that no one uses. And one Friday, you notice that the window's broken. You're like, oh, that's a bit sad, whatever. Go home, the weekend passes, on Monday you walk past and it's like, what? There was this norm setting, the signal that was sent that no one cares. That window got smashed, don't worry about it. And so vandalism kicks in because no one thinks anyone cares about that. That can happen in our code bases. That signaling effect, you say, oh, the build's red, we'll do it on Monday. Yeah, oh, that, we've got some warnings in the code base. I'll sort that later. Really interestingly, in the performance space, that shit didn't fly. That got fixed straight away. I was really impressed that it was all the things we preach, you know, fix the build, single responsibility principle. That was the secret sauce, not get better hardware or something like that, or concurrent all the things. It was the simple stuff. I thought that was really fascinating. So the beauty about our field is that it's applied science. So you don't have to listen to anything I say. It's great. It's not a theoretical science. We can go and prove all this kind of stuff. Is a single producer, single consumer thing faster with a circular buffer? Go home and prove it. Grab benchmark.net or one of the Java tools and find out. Write your own one. This is kind of cool. And this was another thing that I learned when I was in London is we don't have to have a discussion and think about what might be faster. Talk about what product might be better. Is JSON better than protobufs? Why are we talking about it? Open up the laptop. Let's go. Let's find out. This stuff is easy to do. And the more you do it, the better you get at it. And then you read some blogs and you find out someone else has already done it. You pull down their source code and you find out, oh, actually, we run AMD here, and that's not true on AMD. Oh, that is true on Intel. Oh, we're running on Atoms, or we're running on phones. Oh, this is different on this platform. We're in a practical, applied science. You can prove this kind of stuff. It's fun to do. So the top 10, know your targets, know your costs, know your flows, know your subsystems, and know your reasons. Then, once you know your things, justify the cost, be aware of your GCs, ouch, serialize, don't synchronize, circular buffers, and performance culture. More information, actually just grab hold of me. I've got so much, I love talking about this stuff. Do we have time? Yeah, cool. Anyone want to see something funny? Or anyone got questions? Funny thing? I just thought this was so neat.
You're keeping us from funny.
Yeah, so bonus sections. We will not have time for this. Bit twiddling. So we're talking about circular buffers before. If I have a 16-byte array, a 16 size array, and I get to the end on my circular buffer, how do I get back to the start? Well, there's a couple of things we could do. We could do the old, I'm at the tail, and the tail equals the capacity, branch, go back to 0. That's cool. Or I can add 1. So I'm either in the middle, so add 1, or I'm at the end, so go back to the start. That's one option. Or I could use modulus. That sounds kind of cool. So the capacity in the tail, modulus gives me the index. Or I could use a bit mask, and that was kind of cool. I'm like, oh, I haven't done this bit twiddling stuff in a while. Does everyone remember the first chart, know your costs? What was the pretty expensive operation of the math ones? Division. What's modulus? Division with the remainder, isn't it? So that sounds expensive, even though it's very easy to write. That looks really quick. You know what was funny? When I benchmarked this using benchmark.net, it's a free tool. How cool is that? Just go open source and now I can benchmark things. You probably can't read it because projectors in black and purple. 0.4 nanoseconds to do the branch plus add. So add 1, oh, I got to the end, go back to 0. 0.4 nanoseconds. 8 nanoseconds for the modulus, which is probably what we thought. It was 6 nanoseconds for a division, so 8 nanoseconds for a modulus. Bit mask, can't calculate it. 0. Too fast. It's 1 CPU cycle. My God. And we're done. Thanks for having me, guys. If you see Rob Moore about, give him a hug. He's amazing.